In this video, we are going to cover 8 Chapter 12 exercises. Question 1. Which of the following is not a suitable nucleophile for an SN2 reaction? So you have to consider all 4 of these. So that's really something that is either not a nucleophile, that appears to be a nucleophile but is not, or may be less suitable than other 3. So when we consider A, that's phenoxide, looks reasonable, it's pretty strong nucleophile. B, hydroxide, also very strong nucleophile. And C, ethoxide. So A, B, and C are typical strong, very good nucleophiles, alkoxides or hydroxide. D is tertiary butoxide. Even though it is an alkoxide, it's not a good nucleophile because it's sterically hindered. So because of the steric hindrance, species D, tertiary butoxide, is a strong base but weak nucleophile. It's non-nucleophilic base. So it cannot participate in SN2 reactions. So correct answer is 1D. Question number 2. Which of the following compounds does not undergo substitution reactions? All of these are bromides, but typically compound in which an sp2 carbon is attached to bromine does not undergo substitution reactions. Neither SN1 nor SN2. And so when you look at them, A actually is benzylic compound, highly reactive. B is correct answer. That's vinylic. So sp2 carbon attached to bromine, that doesn't undergo substitution reactions. C does, and D. C and D are secondary compounds, secondary bromides, they readily undergo substitution reactions. So correct answer is B. Question number 3. Which of the following represents a correct electron flow in a substitution reaction? So A shows movement of electrons from bromine towards carbon-bromine bond. That doesn't make any sense. That's obviously not right. And that wouldn't give you an ion that is shown here. B shows movement half arrow, but only one half arrow. And so movement of one electron towards bromine doesn't show anything what happens with other electron. And again, that's wrong. If you have half arrow, you need 2 half arrows that point either away from each other for bond breaking or towards each other for bond formation. There can't be just one half arrow. So not correct. C. In this case, you have mix of half arrows and full arrow. So at least that's what it appears to be. I'm not sure whether it's half arrow that's going from OH or full arrow, but either way, that's wrong. Breaking of carbon-bromine bond, that's shown correctly. That's homolytic bond breaking. But in OH2, we have electron pair. To move electron pair, we need full arrow. So I can't see quite well whether this is full arrow or half arrow. Either way, it's wrong. Because free electron pair that would result from breaking of carbon-bromine bond cannot combine with an electron pair. It can only combine with another unpaired electron. And so that's not correct. D. D shows breaking of carbon-bromine bond, and that's heterolytic bond breaking. That's correct. That correctly shows heterolytic bond breaking, where bromine leaves with a free electron pair and results in formation of carbocation. And now that carbocation reacts with a free electron pair, and movement of that free electron pair is shown correctly by curved full arrow. Free electron pair from water. So that's correct. So correct answer is D. What is the mechanism of the following reaction? Here is a reaction of trans 1-bromo-3-methyl cyclopentane with sodium azide. And product is corresponding cis compound where azide group displaces bromine, replaces bromine. We can answer this question, what is the mechanism, even without looking at the 4 possible choices. Clearly, mechanism involves inversion because carbon 1 that is bonded to bromine substituent has underwent inversion of configuration. So reaction occurred on carbon 1 where azide group came from the top. Entry group is azide group. Azide nucleophile came from the top and displaced bromine in an SN2 reaction. So this is an SN2 reaction. If reaction mechanism had been SN1, then intermediate would have been carbocation and substituent nucleophile would have come from the top and the bottom. And even if we didn't get equal amounts of the 2 isomers, cis and trans, we would have had mixture of cis and trans isomers, and that would have pointed to SN1 reaction mechanism. Since we have only one product, and that one product is result of inversion of configuration, reaction mechanism is SN2. C and D actually don't make much sense. Mechanism in general doesn't undergo much change in going from protic to aprotic solvent. Next question, which of the following ethers cannot be prepared in an SN2 reaction? SN2 reaction involves reaction of a nucleophile, in general a strong nucleophile, and that displaces a leaving group. So obviously something is wrong with one of these four reactions where that is unlikely to happen. Let's consider case A. We have phenoxide as a nucleophile and reaction with bromoethane. And in fact, in all of these cases, substrate is bromoethane and leaving group is bromine, good leaving group. Phenoxide anion is a nucleophile, so we would expect this reaction to proceed reasonably well and in good yield. In next case B, we have anion of allyl alcohol, and this allyloxy nucleophile again is strong nucleophile, so we would expect this reaction also to proceed in good yield. Next one, we have propoxy nucleophile or propoxide, and again reaction would be expected to proceed in good yield. Finally, last one is T-butoxy anion, and that anion involves oxygen nucleophile that is rather hindered. Because of the steric hindrance, electron pairs from oxygen cannot be effectively donated to an electrophile to form bond with an electrophile. So interaction with electrophilic carbon is prevented because of the presence of three methyl groups that provide steric hindrance. So it is the case D, reaction D, that would not proceed through an SN2 reaction mechanism. What is a suitable reagent for the following reaction? So we can see that in this case, bromine or bromide is replaced by this anion, SCH3. I say anion because bromine leaves as an ion, so that means it has to be replaced by another anion. And since this is inversion of configuration, then that means that this is SN2 reaction. So it's going to be SCH3 minus anion, and obviously if it's reagent, it has to be accompanied by suitable cation. So a typical answer would involve, let's say, NaSCH3. So you simply write down SCH3 and then add appropriate counterion. So NaSCH3, LiSCH3, or KSCH3, those would be reasonable answers. What is the product of the following reaction sequence? So we have another sequence where we are reacting this compound cis 1-bromo-3-methyl cyclohexane first with sodium iodide. This is SN2 reaction, sodium iodide in acetone. It occurs with inversion of configuration. So product is now trans 1-iodo-3-methyl cyclohexane. And then we carry out reaction with methoxide anion, like sodium methoxide. At room temperature, that's another substitution. And again, it occurs with elimination. So the product is 1-methoxy-3-methyl, cis-1-methoxy-3-methyl cyclohexane. What is important to notice here is that final product is amounts to a substitution of bromine with methoxy group with retention of configuration. And so this is one way how we can carry out reaction with retention of configuration. You know that we can carry out reaction with racemization, that's usually not desired, but if we carry out reaction under SN1 conditions, outcome will be racemization. We can carry out reaction with inversion of configuration, and you can see it in first step if we carry out SN2 reaction. But it may not have occurred to you how to carry out reaction with retention of configuration if we need to. Well, here you can see how we do that. Instead of directly substitute bromine with methoxide, which would have worked, but would have given trans product, so product that is a result of inversion of configuration, we carry out two reactions. So we carry out first that at this step that appears to be redundant, substitution with iodide to get inversion of configuration, and then we carry second inversion of configuration. So with two inversions of configuration, we actually end up with retention of configuration. So this is how we can carry out transformation that occurs with retention of configuration, basically carrying out two SN2 reactions. So simply what we do is we convert leaving group bromide into another leaving group and then carry out the actual desired reaction. What was the starting material for the following reaction? In this reaction, starting material reacts with sodium iodide in acetone to give trio isomer of 2-fluoro-3-iodo-pentane. Sodium iodide in acetone is reagent that is used to convert alkyl halides, specifically alkyl chlorides and alkyl bromides, to corresponding alkyl iodides. Fluorine is a poor leaving group, so alkyl fluorides in general don't react very well in reactions like this, which means that fluorine atom, fluorine substituent in starting material will be unaffected. And we can expect then that starting material contained fluorine. That was 2-fluoropentane with halide substituent on carbon 3, chloro or bromo substituent on carbon 3. Sodium iodide in acetone is reagent that reacts in an SN2 reaction mechanism, which means with inversion of configuration. So if the product is trio product, that means that starting material must have had inverted configuration on carbon 3 and would be erythro product. So suitable starting materials would be erythro 3-bromo-2-fluoropentane or erythro 3-chloro-2-fluoropentane. So this question has two possible correct answers. And this completes chapter 12 exercises.